So now we are going to learn about chi-square test of independence. Chi-square test is mainly used to determine if there is a significant association between two categorical variables. So if you have two categorical variables, and we have studied the definition of categorical variables in the very first class. So if you have two such variables, then the chi-square test of independence helps you in determining whether the two variables are associated or not, whether they are independent or dependent. So if you consider the example of, suppose, your education and your occupation, right? So both are categorical variables, and then if these can be dependent, right? So if you are ruling out independence, then you could conclude that these two variables are associated. Okay, so we use this chi-square test of independence whenever we have to determine the independence between the two categorical variables. So in this case, the null hypothesis is that there is no association between the two variables. It means they are independent. An alternative is that there is an association between the two variables. The assumptions over here are that data must be randomly selected and they must be nominal or ordinal, because we know that categorical variables are of two types, right? Nominal or ordinal. So nominal variables are those in which you have categories, but there is no inherent ordering between those levels, while in ordinal you have an inherent ordering also. Now we need two important terms for understanding the chi-square test. The first term is observed frequencies or observed count. These are the cell frequencies actually observed in the contingency table. So here we will make use of the contingency table that we studied in your, I guess, third week of this course, and we will make those contingency table, and from the contingency table we are going to make inferences about the independence of the two categorical variables. The other term is expected frequency. These are the cell frequencies that one might expect to see in the contingency table if the two variables were in fact independent. Okay, so to understand this, let us consider the following contingency table. So you have two categories over here, success and failure, and this side you have again two categories, group 1 and group 2. These are the observed frequencies A, B, C and D, which are written over here. Then what is your marginal total? Marginals are these, that is A plus C, B plus D, A plus B and C plus D. These are the marginals, and this one is your grand total, A plus B. You add up all the observed frequencies, you will get the total. Now given this setup, if you assume that G1 is the event that it is a case from group 1 and S is the event that it is a success, if you use these notations, then the probability of being in group 1, okay, if you denote probability of being in group 1 as this, then what it will be? It will be the total observations in group 1 divided by the grand total. If you look over here, the total observations in group 1 over here is A plus B. So you divide A plus B with this total. Okay. Likewise, if you have to find the probability of success, so probability of success will be the total number of success divided by the grand total. Again, if you look at this one, the total number of success, you will see in this particular column it is A plus C, and you will divide A plus C by the total. So these are the two probabilities that we have obtained. Now if you are assuming independence between these two, that is under the null hypothesis, joint probability we know that in case of independence is just the product of their individual probabilities or the marginals. So if you have to find the joint probability of this, right, that it is a success and it belongs to the first group, it is same as multiplying these two probabilities that we have obtained just now. Okay. Once you have multiplied it, the expected count for that cell, basically for cell A over here, cell A is the first one, right, corresponding to first row and the first column. So you have to compute expected count. So what you do over here, you multiply the joint probability. So basically this is coming from your joint probability over here, and you multiply it by the grand total. That is the total that you have, right? So basically, why are we doing that? Because we want to see that how many observations you would expect in the cell, that is A, if the two categories are independent. Okay, this is what is meant by the expected count. That is why you are multiplying it by the grand total. Okay, so this first term over here is the product of the two probabilities. Okay, and this one is the grand total. So what you are left with is this, right? So you see that these are the row totals and column totals, and you are multiplying it by the total number of counts. So this expected count reflects the frequency we would anticipate if the two cells, that is G1 and S, these two events were indeed independent. Because G1 and S are what? These are also categories or the levels among your categorical variables. So if these two are independent, then under the null hypothesis, you will find the expected frequency. So if you want to generalize this formula, in the numerator you have the row total and you have the column total, and finally you divide by the grand total. So for each cell you will consider in the numerator you will multiply the row total with the column total, and you will divide by the grand total. So if you see over here, so what we have, these are the row totals, right? So if you have to find for A, what we did is that we divide this A plus B and A plus C, right? This corresponds over here. So let me just use a different color, right? So this, if I am interested in this particular cell, it corresponds to success and group 1. So this is my row total and this is my column total. So I'll multiply these two and divide by this. If I am interested in D, in this cell, which corresponds to this level failure and group 2, what I will do, I will look across this. This is the column total for D and this is the row total. So you will multiply these two and divide by the total in order to get the expected frequency for this. So A, B, C, D, these are the observed frequencies that you have already obtained. From there you will calculate the expected frequencies. For calculating the expected frequencies, the formula is that you have to multiply the corresponding row total and column total and divide by the total count. Okay, so you will get the expected frequencies like this. So if you have R rows and C columns, the total number of cells would be R times C. Okay, so how many observed counts will be there? It will be from O1, if I am using this notation, O1, O2 and so on. Likewise, for expected counts, we can use E-wise. Okay. Then the test statistic, basically, that is the chi-square test statistic, is you have to consider the first observed count, subtract the expected count, take the square and divide by the corresponding expected count. Likewise, you will do for all the cells, and finally what you get is this summation over here. What are we doing here? So first of all, we are considering the squared deviation of the observed and the expected, right? OI minus EI, we are considering these differences and we are squaring it up because there will be some positive term and negative term. So in order that they do not get cancelled, we are taking the square of that, and then we are standardizing it by dividing it by the corresponding EIs, right? Like the way we do for the sample variance or the population variance. There also we divide by n minus 1. So we take summation xi minus x bar square, right? We take whole square and then we divide by the total number of observations. So here also we have O observed, difference of these two, and then we sum it over all the possible cells. So this is the chi-square test statistic that we use for chi-square test of independence. Okay. So you have the observed counts, you have the expected ones, you perform this, find this chi-square test statistic, and then you find the critical value. So under the null hypothesis, it would follow chi-square with R minus 1 into C minus 1 degrees of freedom, because R is the number of rows and C is the number of columns. So if I have to find the degrees of freedom, so it will be basically R minus 1 into C minus 1. You compare these two values, and if you find that your calculated value or the calculated test statistic that you have obtained is less than the critical value chi-square, this one, then you fail to reject the null hypothesis. Otherwise, you would reject the null hypothesis. It means that if your chi-square value, this test statistic, comes out to be greater than this chi-square alpha value, then you reject the null hypothesis. Okay, so this is the idea or the background behind your chi-square test of independence. So you'll consider two categorical variables. They will have certain levels. You will have the observed frequencies from the contingency table. You can easily find their expected frequencies as we have done just now. Row total multiplied by column total divided by the total. And you can then calculate your chi-square test statistic also, which we have the formula in the previous slide. And then you will compare it with the critical value as we do in hypothesis testing problems. So let us consider an example over here. Suppose you survey 300 customers on their favorite movie genre, action, comedy or drama. So these are the three categories that you have. And you have the education level. Education level can be high school, undergraduate and graduate, and genres are basically action, comedy and drama. So three categories or three levels in both the categorical variables. So if you look at the column totals, if you add these three, you would get 100, and likewise here it would come out as 120 and 80 over here. Likewise the row total would be these. And this is the total number of observations. You have to determine whether there is an association between the education level and the preferred movie genre. Okay. To do this, you have these as the observed frequencies, right? These are the observed ones. You have to find the expected ones from here. So first of all, what is the null hypothesis? The null hypothesis is that there is no association between the level of education and the movie genre preference, versus your alternative that there is an association between these two categorical variables. Expected frequencies, we know that it will be the corresponding for ith row and jth column. You will take the ith row total and multiply it with the jth column total and divide by the grand total. So if I consider high school and action, so this corresponding cell is the total high schools and total action, that is the row total and column total, and you divide by the grand total. So here it is 120 into 100 divided by 300. So what is it? Basically we are looking at this particular observation over here. So it corresponds to high school and action over here. So what we have to see? We have to see this column total and this row total, 120 into 100 divided by 300. Likewise, if I see this one, this corresponds to high school and comedy, right? This preference. And if I have to find the expected one, we will multiply 120 by 120 over here, divide by 300. Likewise, we can find for each of these, right? So there would be 9 such expected frequencies. Okay. For instance, if I have to calculate for 40 over here, 40 corresponds to undergraduate and drama. Okay, so here if I have to find the expected frequencies, I will multiply 80 by into 120. You have to multiply these two and you have to divide by 300 over here. So this is how you do it. And finally, if you want to summarize it for all of them, these are the expected frequencies that you can get by using this formula. So I have shown it only for 2 and written and summarized for rest of these cells, 7 cells. So you have these as the expected frequencies. Now you have the observed frequency, you have the expected frequencies. You can calculate your chi-square test statistic. So chi-square test statistic will be what? The first observed one for the particular cell that corresponds to high school and action. Its corresponding observed frequency, you will subtract from that your expected frequency, take the whole square of that, and you divide by the corresponding E, because it is OI minus expected one whole square divided by EI, and you sum up for all the cells. So in this case, we have from I1 to 9, right? OI, if you have, so basically we are writing this as high school and action, then it will be for high school comedy. Likewise, if you go on, you will get 9 such values, 9 such terms, you add it up, and finally what you get is 29.38 approximately. So you have obtained the chi-square test statistic. Degrees of freedom would be, R is your 3, number of rows, number of columns is also 3. So it would be, the degrees of freedom would be R minus 1 into C minus 1. So which basically means 2 into 2, what you get is 4. And if you look at the corresponding p-value, so here it comes out as 6.56. You can use basically the p-value approach, and you can find this using your software, or if you're using the rejection region approach also, so that also can be used. If you have the critical value for chi-square value at 4 degrees of freedom and alpha at 0.05, so this value if you have, you will compare it with your test statistic that you have obtained just now, that is 29.38. Okay. Since this p-value is so low, obviously it is going to be less than 0.01 or 0.05. So you reject the null hypothesis that there is no association between these two, and it signifies that the two categorical variables are associated or they are not independent. Okay. So this is how you perform chi-square test of independence. The next test that we have is the chi-square goodness of fit test. Now the chi-square goodness of fit test, what it does is that it tests whether the sample data that you have, it is coming from a population with a specified distribution or not. So it evaluates how well your observed data fit a specified distribution. Okay, so it will compare your observed distribution with the expected distribution and see if there is a significant difference between them or not. Okay, so it compares the observed frequencies in each category to the frequencies we would expect if the null hypothesis were true. So basically observed and the expected ones will be compared. So the null hypothesis will be that the observed distribution fits the expected, and the alternative will be that it does not fit the expected one. So these are your null and alternative. What will be your expected value over here? Expected value in this case is EI into n times PI. So this is a way you calculate your expected frequency for each category. Okay. N is the total number of observations in the sample, and it is the hypothesized probability of an observation falling into the ith category, right? Because for each category we would expect to have the same proportion of as they have when if you are not preferring any particular category in the null hypothesis. So this hypothesized probability is based on the expected distribution. We are comparing our data against that. Okay, so observed frequencies are there. You will calculate your expected frequencies for each data. So expected, in this case it would be n times PI, and this chi-square test statistic, the same thing would be there as we obtained in the previous one, and here the degrees of freedom would be k minus 1. So if the total number of categories is k, you take it as k minus 1. So if you get a high chi-square statistic, it would indicate greater difference between observed and expected values, right? Because you are taking difference of the two, you are squaring it up and dividing by EIs. So if higher value means that observed and expected are very far away from each other, suggesting that the data do not fit the null hypothesis well, right? Or the distribution that we are expecting. So you compare the chi-square value to the critical value at the desired significance level, or you find the p-value. If the critical value or the calculated value exceeds the critical value, or if the p-value is less than the desired significance level, we reject the null hypothesis and suggest that the observed data is not consistent with the expected distribution under the null hypothesis. So this is how you perform chi-square goodness of fit test. Okay, so here you have to see whether the sample data set that you have obtained is coming from the specified distribution or not. Okay, to understand this, let us consider the example over here. So a movie theater surveyed 90 customers to find out their favorite movie genre, action, comedy or drama, and this is the observed frequency that they obtained for each of these levels. The goal is to determine if there is a significant evidence suggesting that the preferences for movie genre are not evenly distributed among the customers. So you see that here the categorical variables has 3 categories. Had it been like 2 categories only, we could easily use your proportion, 1 proportion sample Z test, right? Because in that case, if you see 1 proportion, what do we consider? It is p hat is x by n. So x is the number of individuals who have that characteristic and n is the total number of individuals. So the total number of individuals can be categorized into 2. The first one is those who have that characteristic and the other one is that those who do not have that characteristic. So basically there you have 2 levels only, 2 categories. Okay, so if you have just 2 categories, then your 1 proportion test would also be applicable. But if you have more than 2 levels, like 3 in this case, you have 3 levels or more than that, then in such situations chi-square test of goodness of fit test can be used. Obviously you can use chi-square goodness of fit even if there are only 2 categories, but here we are specifying it. If there are 3 categories, then it is better to use it, 3 or more. So in order to find the solution to this, what we will do? These are the observed frequencies. First of all, we will write the null hypothesis and the alternative one. Since here the hypothesized proportion for each genre is 1 by 3, and if you sum it up, it would be 1, right? So here in this case, if you denote the proportion of preference for action, comedy or drama by these notations, you will have this. So the null hypothesis in this case would be that the 3 have equal proportion, that is 1 by 3, and in this case that at least one of them is not 1 by 3. So the proportion is different in this case. Okay, obviously each of them has an equal chance of occurrence, so 1 by 3, you add it up, you will get a 1. The expected count for each genre will be what? It will be n times pi. So n is 90 and pi for each of them under the null hypothesis is 1 by 3, because for each category you would expect to have 1/3 of the total sample. Okay, as there is no evidence to prefer any one category, right? If you want to prefer one level more. So since we are considering that they are same, so they are equally, they are preferable, so that is why we consider them as 1 by 3 under the null hypothesis. Each of them have an equal chance of occurrence. So the corresponding chi-square statistic would be, since they are 3 levels only, so I 1 2 3. So this is the observed one, this is the expected value. So EIs in each of them you will have n times pi. So each of cases E would be same, right? N times pi basically means that 90 into 1 by 3, right? So 30 in all the cases. That is why you see in all these terms you have 30. And finally, when you substitute the value, you have 4.99. Okay. Now, with 2 degrees of freedom, the p-value, if you calculate the p-value, it is approximately 0.0825. Or if you want, you can look at the critical value also. So you will look at chi-square value at 2 degrees of freedom, and suppose level of significance is 0.05, you will find that value and you will compare the chi-square test statistic that we have just obtained, which is 4.99 with that critical value. Now in this case I have written for the p-value, so you can compare p-value with 0.05. You can see that p-value is greater than alpha. So you do not reject the null hypothesis. You fail to reject the null hypothesis and conclude that there is insufficient evidence to suggest that the preference for movie genre among theatre patrons are unevenly distributed. So you fail to reject the null hypothesis. That is, null hypothesis was that the three proportions are same as 1/3. Right? So here you fail to reject it. You cannot say that one is preferred over the other. It is not unevenly distributed. So this completes the theory part of the 9th week. In the next lecture, we will look at the Python codes for these concepts. And in the next week, we are going to learn about your bootstrap method for hypothesis testing, and which will be followed by your confidence interval estimation. So if you can recollect what we have studied in this week, so we started with your hypothesis testing for two sample problems. We considered for difference of two means, then we had two variances, two proportions. Okay, so in all three cases, we found out how to test the claim that has been made about the population parameter. And then in addition to those, we also studied two important tests, that is chi-square goodness of fit test and chi-square test of independence. Okay, so these are very much useful. This completes our theory part of this week. Thank you.